This is 2.4 functions. You might remember that a function means that each x value has a unique y value. Sometimes we say input and output for x and y. So we're not going to have our x values repeating. A function also has to pass the vertical line test, kind of for that same reason, because each x can only have one y. So we're going to start by graphing some points. At any time, you might want to pause the video so you can write down some important features of the function, like these things that I mentioned here, because I'm going to move pretty fast. You might have to pause to be able to get it down fast enough. All right, so I want you to start by graphing those 4 points and using the vertical line test to determine whether or not it's a function. When we graph them, if we draw a vertical line, any vertical line is only going to pass through at most 1 point. So we would say, when it says, is it a function? Yes. It passes the vertical line test. And when it says why or why not, we want to explain what that vertical line test means. So we need to say that no vertical line passes through more than 1 point. All right, so let's try another one of those. Again, I would like for you to pause it, graph it, do the vertical line, write your statement, and then come back and see if you got it correct. Let's take a look at number 2. So please graph those. And then draw your vertical lines. In this case, since our x values repeated, we would say that no, it is not a function because it does not pass the vertical line test. I misspelled does. Doesn't pass the vertical line test. And why is that? Why does it not pass? Well, because a vertical line passes through more than 1 point. On this particular graph, there's actually 2 different vertical lines that pass through more than 1 point. You don't have to have 2 that do it. We really only need 1 vertical line that passes through more than 1 point, and if there's 1 vertical line that does that, that makes the whole thing not a function. Now, most of the time, we don't look at just individual points like this. Most of the time, we're looking at a relation, and we'll determine if something's a function after we make a table of values and graph it. Most of us, when we look at y equals x squared, recognize that it's going to be parabola shaped. So when we make our graph, we first need to make a table. And you can put any numbers you want in a table. I would always recommend to do some negative, some positive, and 0 to get a good representation, especially if you don't know what it looks like. So if you didn't know that this was supposed to be a parabola, you would definitely want to have more points so that you could start to see the shape of the graph coming to life. We can see that parabola shows up there, and then we can go over the domain and range. Domain is our x values. Domain is always left to right. So as we come in from the left, we hit an arrow, meaning negative infinity. So we can put any number in for x right there, from negative infinity all the way to infinity. Range is our y values, and when on the graph, we always go bottom to top for our range. And the bottom of our graph, in this case, is at 0. The top is heading up to infinity, so we'd say 0 to infinity. Now this graph is a function because if we drew vertical lines, there is no place where it would go through more than 1 point. So it is a function. Now this next one, most people aren't as familiar with. Y squared equals x. Most people don't know what that looks like from the beginning. So this is one of those cases where you will need to build a table and put enough points in the table to figure out the shape. So go ahead and hit pause, try to build your table, graph it, and then come back and check and see if you did it right. Since I'm building this one and it's y squared, I'm going to put numbers in on the y side this time. So I'm going to do -2, -1, 0, 1, 2, just like I did up on the first one, but on the y. So I'm going to take -2 and square it to get 4. -1 squared, 1. You'll notice it's the same points, they're just switched from that first one. So when I go to graph it, instead of it being a parabola opening up, it is going to be a graph that looks like a parabola opening to the side. Now, this one is not a function because if we were to draw a vertical line, it would go through our relation more than once. But we still can state the domain and range. Domain goes from 0 to infinity, range -infinity to infinity. So it's the opposite of number 3. They just all kind of switched on those. All right, now the next one I'm going to show you is even more strange. You definitely probably don't know the shape of it. So again, the table is going to be really important. So make sure you hit pause, try to build your table, and then come back and see if you got it right. Here we have number 5. When you're building your table, make sure you put in enough values to have a good sense of what the whole thing looks like. It is okay to get decimals as you're working on your table. On this one, if you put in any number greater than 2 or less than -2, you get an error. And that's because this function is very unique in its shape. It is only above the x-axis. It's just like a little half of a circle. So its domain starts here and ends here. So it starts at -2 and ends at 2. Its range starts at 0 and goes up to 2. Now the reason that I knew that it did that is because I tried -3 and 3 and those didn't work. But I also used something that we learned in section 1.2. If you want to look back in your notes from section 1.2, we talked about how radicals have to be greater than or equal to 0. So 4 minus x squared has to be greater than or equal to 0. So 4 has to be greater than or equal to x squared. And then when we take the square root of that, we get our 2 and also your -2. So it's kind of written backwards right now. But that tells us that our numbers that we have to put in have to be between -2 and 2. So you may not have remembered that from 1.2, and that's okay. But if you just test points in your table, you would come to that same conclusion, that they all would have to be between -2 and 2. All right, now number 6, again, may not have any idea what this looks like, so you're going to build a table. So hit pause, put some numbers in, see if you can come up with what basic shape it might be. I always try to find numbers that work out nicely. So since this is a cube root, I might try to find numbers that I could easily take the cube root of. But if you find ones that are decimals, that's okay too. I'll throw a few of those in my table as well so you can kind of see. Kids always ask, why did you use -8? Well, because I knew the cube root of -8 is -2. Same thing for 8. I knew that 8, oops, that's 9. I knew that 8, when I take the cube root of it, was going to give me 2. So it was going to give me something nice. Now, you don't necessarily have to use that. That's just kind of thinking ahead of what numbers to put in that'll end up working out pretty well for you. Once you plot all your values, you get a sideways cubic, which kind of looks like a little S curve. I call this the Egyptian. The domain is all real numbers like other cubics, and so is the range. So even though this is a cube root, it has the same domain and range as a cubic. And both of these, both 5 and 6, are functions, because if we draw a vertical line test, neither one would have a vertical line going through more than one point. All right, let's switch it up a bit. Now we're going to evaluate. Evaluate means that we take this number in the parentheses and we put it in for x. So on this first one, we are going to put a 3 in for the x there, and then we'll simplify. So we have a 9 minus 4, which gives us 5 over 5, so we get 1. Now on the next one, we don't just have a 3, now we have a d. When we put that into the function, the whole 3d is squared. So not just the d, not just the 3, but the whole thing. So we have to square the 3 to get 9, and we also have to square the d to get d squared. Once we do that, there isn't anything more we can do to simplify. So we have to leave our answer just like that. Part C, we're going to substitute d minus 2 in for the x squared. Since this is a binomial, two terms being squared, we have to remember that squaring means multiplying by itself. So d minus 2 times d minus 2 minus 4. And then you can FOIL it out and simplify. When I FOIL that, I get d squared minus 4d plus 4 minus 4. That minus 4 was already there. So simplifies to 5 over d squared minus 4d. Part D says give f of x domain and interval notation. Okay, so this again goes back to section 1.2, just like we talked about before, where we looked at fractions and we said we can't have a 0 in the denominator. So we say x squared minus 4 can't equal 0. Add 4 and then take the square root, so we find out that x cannot be positive or negative 2. Remember, when we take the square root, you have to have a plus or minus sign. So if it can't be positive or negative 2, that means it can be every other number. So when we go to write it in interval notation, we're going to start at negative infinity. We're going to go all the way up to the first number that it says it can't be. That's negative 2. Then we're going to put a union. We're going to start again at negative 2 and go up to the next number it can't be, which is 2, and then put a union, and then go 2 to infinity. So this tells us that all numbers are possible except for negative 2 and 2. The last two examples that we are going to do are just, again, review from section 1.2. So a lot of just being able to find the domain. So see if you can write these down, hit pause, try it on your own, and then come back and check. Because number 8 is just like the one we did on number 5, where I showed you how to take that radicand and set it greater than or equal to 0. So we have 4x minus 3 is greater than or equal to 0. We're going to solve that to find out that, oops, that would be 3 there. The x is greater than or equal to 3/4. When we did this in section 1.2, one of the suggestions was to put this on a number line to kind of visualize what we're talking about. If we're saying x is greater than 3/4, that means everything to the right of 3/4. So when we write that in interval notation, we say bracket 3/4 to infinity. Now notice this time we only have one interval, whereas on the last question we had 3 intervals. So it definitely depends on the situation. So try to do that same thing on number 9. Take that radicand and set it greater than or equal to 0, because we want to keep anything under a radical positive, and numbers greater than or equal to 0 are positive. That's why we're doing that. And they're going to solve. Some people probably subtract 6 and divide by negative 5. I like adding the 5x over but you should get the same answer either way. Don't forget though that if you divide by a -5, you have to flip the sign. If you do it my way, you're gonna have to flip the sign at the end because your x has to be on the left side. So if we were to sketch a picture of this one, our 6/5, it says x is less than that. So everything to the left. So that would be -infinity to 6/5 with a bracket. So again, just one interval. So most of the time when we have a radical, we just have one interval, opposed to the other one when we had a fraction, you usually have more than one interval.